All right, in this video, we're looking at standard 8.3b. Calculate the rate of change of a linear function represented in a table, graph, or algebraically in context of math and real-world problems. Basically, we're dealing with rate of change. We are dealing with slope. That is what we are dealing with today. And so I'll put this little reminder here. Use your formula chart, because this guy right here, the slope of a line is perfect for finding rate of change. It's really just the difference of y's, or the change in y over the change in x. We also often call that change of y rise and our change in x run whenever we're looking at a graph. Okay, and so here's our little formula for finding that. Subtract the y's and then divide by the difference of the x's. So starting here, what's the slope of the line that passes through these points? Once again, I'm just finding the slope. Here's my slope formula in my formula chart. So I'm just going to label my points. I'm going to call them x1, y1, and x2, y2. Honestly, it doesn't matter if I call this x1, y1 and this x2, y2, or the reverse. I could call this second point x1, y1 and the first point x2, y2, and it wouldn't matter. But basically, I'm just going to use the formula from my formula chart to find that slope. And in this case, my y2 is 12, my y1 is 7, my x2 is negative 39, my x1 is 26. So if I subtract in my numerator, 12 minus 7 is 5. If I subtract in my denominator, let's see, I need my calculator for that. Negative 39 minus 26 is negative 65. Now, as you can see, I don't have that option here, but this slope can simplify. This rate of change can simplify. If I divide a 5 out of my numerator, and then if I divide a 5 out of my denominator, I end up with negative 1 over 13, which would be answer choice A. Let's say you drew a blank on your test, had no idea how to use this formula to find slope. You could plot these points on a piece of graph paper, and you have to get a pretty big graph paper to plot those. But if I were to do, let's say the point 26.7 is right there, and the point negative 39.12 would be, say, like right there, and you can just count rise over run and see what you get. But this one's a little bit tough to do that because these points are so large, so you can rely on your formula there. Table represents some points. Got some points. What is the rate of change of y with respect to x? Now, it's going to word it like this a lot. We're going to see that in the following problems. Rate of change of y with respect to x. All that means is rate of change. All that means is change of y with respect to x. In other words, y2 minus y1 over x2 minus x1. The rate of change of y with respect to x is all this is asking for. So if this is linear, that means the slope between the first 2 points should be the same as the slope between the next 2 points. If this was exponential or quadratic, that wouldn't be the case, but our rate of change should be the same everywhere. So in that case, I'm just going to calculate the rate of change using these first 2 points since there's no decimals involved in the first two. So if I do y2 minus y1 over x2 minus x1, I should be dealing with y2 minus y1 over x2 minus x1. And be careful not to lose your minus there. It's x2 minus x1, and your x1 is a negative. So you got to have minus a negative there. If I were to simplify, my numerator becomes negative 9. My denominator becomes 2. Bam. That's our answer. Now, this problem, same idea. They give us a graph. And this says, what is the rate of change of the balance, of the balance with respect to the number of deposits? So they're just telling you, that's wording a little bit funny, but it's really just asking for rate of change. It's really just asking for slope again, but with balance being your y and number of deposits being your x. In other words, what is our change in y over change in x? Now, I could pick a couple of ordered pairs here from the table. Like, for example, we have the ordered pair 0, 50, and there we have the ordered pair 1, 150. And I could do y2 minus y1 over x2 minus x1, but I can also just do rise over run, okay? So from a graph, know that you can find the slope by finding your rise over your run. So if I were to start here, and I'm trying to go to here, we can rise 100 because you got to notice your scale. We don't rise 2, we're rising 100. So if we rise 100, we run 1. In other words, we rise 100, we run 1. Okay? So basically, it's $100 per deposit because our Y is a dollar amount, right? That's a balance. So our change in Y would be the change in the balance. And then our run is the number of deposits. So this is the balance would change by $100 for every deposit. That's why I like answer choice A on that question. You would have gotten answer choice D if you didn't notice the scale on the y-axis. Although we're rising 2 blocks, that's the equivalent of rising $100, okay? Which of these best represents the rate of change of the volume of the gas, the rate of change of Y, with respect to the temperature X? Now, once again, we don't really have to be able to interpret the wording because we know that our Y is on our Y-axis and our X is on our X-axis. And so, but here, just the wording. If they say rate of change of volume with respect to temperature, they're telling us that volume of the gas is Y, respect to the temperature is X. So here, if we're doing rise over run, the tricky part about this problem is identifying good points to use, because I'm trying to find where that line crosses at a perfect intersection of points. And it's really hard to find the perfect spot. Ooh, that looks like a good point right there. But let's see, if I'm looking at it, I think I like that point right there. And if I'm being super nitpicky, even some of these points like that one look like they might just be a little bit off. So, let's see. I think that looks like a good one. I don't really know what else. There's not a whole lot of good points, so I would go with those two. And so from there, let's see. If I'm counting my rise over run, 1, 2, 3, 4, 5, and my run is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I would think it would be 5 over 12. However, we got to notice our scale. Okay? Our scale on our y-axis is going up by 1. So if we rise 5, we really do rise 5. However, if we run 12, notice the scale on our x-axis here. Okay? It looks like I'm starting at 30 on the x-axis. This looks like 30, and I'm going to 90. So our scale is really going by, what is that, 5s? 25, 30, 35, 40. So if I'm running from 30 to 90, we know my run is actually 6. If I'm looking at this, is 60, excuse me. But if we have 12 units that we're running, and each one of those units represents 5, we could calculate it that way as well, because 5 times 12 would give us that run of 60 as well. So if we're finding the rate of change of y, or excuse me, the change of y over change of x, that's going to be our change in volume over our change in temp. And we've already established by looking at our graph as our volume increases by 5 milliliters, our temperature increases by 60 degrees. Okay? So basically our answer is 5 over 60, but if I look at my answer choices, I don't see 5 over 60 anywhere, but lo and behold, 5 over 60 simplifies to 1/12. Bam!